conference. It's been great so far, and I'm sure it's going to be great the rest of the week. Thank you guys for coming so early in the morning. I hope you guys are more awake than me. I'll still try to say something coherent. And the plan is, I'll try to tell you a bit about tropical ideals, which are these combinatorial, very matroidal objects that kind of arise naturally in tropical geometry. And I'm not going to assume that you have heard of tropical geometry or know anything about tropical geometry. I'll just try to tell you like the very matroidal picture that we get from tropical geometry, okay? So, yeah. So the thing you need to know, or a good, if you want to think of tropical geometry, it's just think of it as a tool that algebraic geometers use for turning algebraic varieties into combinatorial objects, okay? So some algebraic geometer might be interested in studying this cubic curve in the plane, and then using the tropical geometry machinery that I'll tell you a bit more about, you turn it into some kind of combinatorial, polyhedral-looking object that still preserves some information about the original variety, and then by studying the combinatorics of this polyhedral object, you can start to understand something about your algebraic variety, okay? So how is this process? Let me tell you the bit that we need about this tropicalization process so that you see where tropical ideals arise. Well, suppose we want to tropicalize the zero locus of some ideal of polynomials with coefficients in a field, okay? So J is some ideal of polynomials in the variables x1 up to xn with coefficients in the field k. And we want to tropicalize it, tropicalize the zero locus of that ideal. So what we're going to do is, first, for every polynomial, whenever you have a polynomial, so coefficients times some monomial, and I'm using bold U to denote the exponents, the vector of exponents in the monomial. First of all, I'm going to call the support of the polynomials to be the monomials that actually appear in the polynomial with a non-zero coefficient, okay? So it's just the set of lattice points that correspond to the monomials that you see in your polynomial. That's the support. And then I'm going to call this the tropicalization of the ideal itself, the whole collection of polynomials, to be just the collection of supports of polynomials that are in your ideal J, okay? So the tropicalization of the ideal is going to be a collection of subsets of n to the n. So each of these is a finite subset of the n-dimensional lattice of n to the n, and then you have a bunch of those. So once you have that combinatorial information, the collection of all supports in your of polynomials in your ideal, you can define the tropicalization of your variety, of your zero locus, to be just the set of directions A in R to the n, such that for every support, for every element here in this tropicalization of J, the maximum direction, so when you maximize the element of S in the direction A, that's attained by at least 2 terms in S, okay? I'll give you an example of this in just a second. Yeah, exactly, so right now. So just to make that very clear and so that we're all in the same page, let's say we want to tropicalize a very simple variety, a line in the plane. So for example, the line given by x plus y plus 1 equals 0, right, with coefficients in some field k. So how do we do this process that I just described to you? Well, first you take your ideal J of all polynomials in the ideal. So ideal, remember, means you close it under multiples of this and under addition. So you have the generator, for instance, but you also have x times the generator, y times the generator, and maybe this one minus that one, which I believe is, this one minus that one is this one, and so on. So you have an infinite collection, all possible multiples of this polynomial here. Then you tropicalize this. This is your ideal with coefficients in the field k. You tropicalize it, you combinatorialize it by taking only the supports. So for instance, you see what monomials appear in this first polynomial, and you see 3 monomials, the constant monomial, the monomial x, and the monomial y. And technically, I'm thinking of these as a subset of 3 lattice points, like this lattice point, if this is n squared, then I'm taking these 3 lattice points. Yeah, the constant monomial would be the lattice point 0, 0. X would be 1, 0, and y would be 0, 1. I identify monomials with the exponents. And you do the same for all these polynomials here. So the second one, you take the support. What monomials appear there? It's just these 3 monomials. Basically, you ignore coefficients. Yeah, so you just take the monomials. And now once you have this tropicalization here, this collection of lattice points, of subsets of lattice points, then you look at the directions in which, for each of these, the maximum dot product with each of these is attained twice. So for instance, for this subset of 3 points, you look at all directions in which, when you maximize the dot product with these 3, you get at least 2 terms, and then you see there's exactly 3 directions that do that, right? So this direction, that's exactly perpendicular to that edge, and that's all these directions here, or exactly going vertically down, and then you maximize, the dot product is maximized by these 2 terms, or going exactly to the left, and then the maximum is attained by these 2 terms. Any other direction that you pick, the maximum is attained only by 1 term, so you would not include that in the tropicalization. Yeah? So this is a tropical line, and Graham was telling us yesterday how to start with a matroid and construct a Bergman fan of the matroid, a matroid fan. That's exactly what we did for the matroid realized by this subspace. So U2, 3 would tropicalize. This would be the matroid fan associated to that matroid. Yeah, does that make sense? Good. So that's all the background we need from tropical geometry. Maybe I'll say, one of the basic theorems that people use in tropical geometry is that actually is not completely obvious, but what you get here is a finite polyhedral object, a finite polyhedral fan. So a fan is just a collection of cones. A cone is just the positive span of some vectors. And then what you get here is a union of cones, some collection of cones. That's what a fan means. So here we see 3 cones, this cone, this cone, and this cone. That's a fan. And actually, it's really non-trivial, but it's true that the polyhedral complex that you get here has exactly the same dimension as the algebraic variety that you started with. So this was a line in P2, and a line is 1-dimensional. Therefore, when you tropicalize it, you get a collection of cones that are 1-dimensional. Yeah, so dimension, for instance, is preserved, and there are many other properties that are preserved, but for what I'm going to tell you about, this is enough. So you get some finite polyhedral object. The finiteness is not clear at all, because you have infinitely many conditions, but yeah, and of the same dimension. All right? So that's all we need to know about tropical geometry for this. And then what is this thing about tropical ideals? Well, turns out that, tropical geometry, I would say, has been around for maybe 20, 30 years now, and at least in the current form that we have it. And at the beginning, studying tropical geometry was really studying the varieties, so meaning studying this picture here. So studying polyhedral objects and how they intersect, yeah. But then the proposal that, together with Diane McLagan, we made in this paper in 2016 is, well, why don't we focus instead on this more directly, like, algebraic combinatorial object in the middle? Let me go back to, why don't we focus on this collection of supports of all polynomials that appear in your ideal? So that's strictly more information than that. From this, you can recover the variety, the polyhedral object. But this thing itself is interesting, and let's try to focus on that. And I know it's early in the morning, but I'm going to try to have some audience participation here. So let's try to think. Of course, not every collection of finite subsets can appear as the collection of subsets of the collection of supports of an ideal. There's some structure in this thing in the middle of this collection of lattice points that we saw. And I'm going to try to see if you guys can suggest some properties that this collection of subsets of lattice points should satisfy. I'm going to start giving a first property, kind of trivial, that this should satisfy, which is that the empty set needs to be in that collection because 0 is a polynomial in your ideal, and there are no monomials appearing in the polynomial 0. So 0 has to be in this tropicalization of your ideal. Can you guys tell me some other property that this collection of lattice points, this collection of subsets of lattice points satisfies? Yeah, Jensen. If you have a subset, then any shift of it to the right or up should also be in that collection. That's exactly right. So if you have a subset in your ideal, then when you add a coordinate EI, meaning you add to all the lattice points appearing there, that should also be there. And that's because the thing you started with was an ideal, meaning it was closed under multiplication by the variables. So whenever you have a polynomial, if you multiply it by x, then all the support just shifts to 1 to the right. And you can multiply by any variable. Yeah. Any other suggestions for properties that this collection should satisfy? Yeah, different. Yeah. Sorry? It's closed under sums, and sums, when you take sums of polynomials, at least if it's a generic sum. Sorry, say again? It's not necessarily closed under Minkowski sum because there can be some cancellation when you multiply the polynomials. But I mean, very related to what you're saying is that it's closed under unions. And that's because when you take two polynomials in your ideal, you can add them. And if, at least if your field is infinite, you can take just a generic combination of the two, a generic linear combination of the two polynomials, and then the support that you will see in that combination is just the union of the two supports that you had. It's from this one and this one, you get something like the Minkowski sum. And there's one last one that for us in this conference is kind of interesting, which is, can you guys see another property that this should satisfy? Well, it satisfies some kind of matroidal exchange, right? And if you think about it, it's because if you have two polynomials in your ideal, and let's say the two polynomials share a common monomial, there's one lattice point that appears in both, then there should be some way of eliminating that monomial by taking a combination of the two. So yeah, you take this polynomial has the monomial u, this polynomial has the monomial u, and maybe you can take the difference, you make them have the same coefficient and take the difference, and then somehow you created a polynomial that has support S3 containing the union of the two polynomials that you started with, the two supports that you started with. It doesn't contain the monomial that was common to the two polynomials, but if a monomial appeared in only one of the two, then it appears in this difference that you created, okay? So this should feel familiar, like some kind of elimination axiom for matroids, and it is actually. So, well, first of all, the proposal is that, okay, these are clearly properties that these objects coming from tropical geometry satisfy, these purely combinatorial properties. How about we forget about this coming from an ideal with coefficients in a field and just call any collection of subsets of lattice points, of finite subsets of n to the n, satisfying these four axioms, let's call it a tropical ideal, some kind of interesting tropical combinatorial object that we carry in tropical geometry. And the ones that do come as arising from an ideal with coefficients in a field, let's call them realizable or representable by an actual ideal with coefficients in a field, just very much like we do for matroids, right? Just trying to abstract the notion of what it is to be a collection of subsets of supports of polynomials in an ideal. And yeah, so how is this related to matroids exactly? Well, it turns out that I mean, if you truncate your subset to consider only monomials of degree at most d, so fix some degree and truncate your subsets to just be contained in that subset of monomials of degree at most d, then when you consider, yeah, the subsets that are contained in there, consisting of monomials of size at most d, of degree at most d, then this is exactly, I mean, these axioms are characterizing exactly the set of cycles of a matroid. Cycles, I mean like unions of circuits, right? So this is, yeah, unions of circuits, the empty set is there, unions of circuits are closed under union, and unions of circuits satisfy this sort of elimination-looking axiom for cycles, which is, yeah, like 0, 2, and 3 are exactly characterizing cycles in a matroid, okay? If you look up in one of these books, yeah, the cryptomorphisms in terms of cycles, you'll see 0, 2, and 3. And then, so basically, this is just saying the collection of subsets is a matroid, except that there is this kind of compatibility or invariance under translation, right? So one way of thinking about it is that a tropical ideal is going to be, well, if you have the matroid that tells you the polynomials of degree 1, then the matroid that tells you the polynomials of degree 2, which is on a ground set that is slightly bigger, then polynomials of degree 3, degree 4, and so on. So you have like an infinite collection of matroids where the ground sets are expanding. Yeah, so the ground set of the first one would be just these three monomials. Then the next one would have ground set these monomials of degree 2, and so on. And you have this tower of matrices that tells you what the whole structure is in the end. But it needs to be, they need to be compatible in the sense of T1. That if you have a cycle, a union of circuits in this matrix, and you move it up, then you should see a union of cycles in the next matrix. But that's one way of thinking what a tropical ideal is. Given that we've been talking about infinite matrices, another way, and yeah, modulus of, if you assume that the original thing was saturated, if you know what that means. Another way of saying this is that a tropical ideal is just a finitary matrix on the infinite lattice on n to the n. So finitary means that the circuits are finite because all these sets are finite. And then you just require that it's invariant by translation by n to the n. Yes?
Are all tropical ideals realizable?
No, that's a great question. So not all tropical ideals are realizable. Let me see how I'm doing one time. Okay, yeah. So yeah, the first question would be, okay, this is this kind of natural definition. Is it maybe true that all tropical ideals are realizable, or are they more than just things coming from ideals? Yes? I mean, I'm presenting the purely distilled matroidal version, but there's a more general version with coefficients, and which really is like an ideal in some tropical ring of polynomials, and then that's why it's called tropical ideals. But yeah, maybe I don't have time to go exactly over one example of a non-realizable tropical ideals, but I mean, you can definitely construct examples of collections of subsets satisfying the four properties, and you can check that actually it's impossible for that to be the support of some ideal with coefficients in a field. Here I had one example. You can ask me later if you're really interested in this. But doing more examples, and then also work that Alex Fink has done, for instance, the expectation is that most tropical ideals are not realizable, just like with matrices. Most matrices are not representable here. We also expect the same to be the case. Even though it's more complicated, it's like a tower of matrices, but still the same behavior should hold. So, okay, so I told you the definition. Hopefully that gives you some feeling of what these subjects are about. And then I'm gonna tell you that there's also, like this kind of simple looking definition can give you a lot, can take you a long way, and you can really prove lots of nice things that should be reminiscent of ideals with coefficients in a field. So for instance, one thing you can do is you can define the Hilbert function of these objects. What's the Hilbert function? Is just the function that for every degree d, it tells you how big the matrix is in degree d, meaning what the rank of that matrix is. So MD is just truncate the ideal to monomials of degree at most d, and then the Hilbert function for a degree d gives you what the rank of that matrix is. So yeah, in terms of basis, well, it's the size of any basis, and a basis is a subset of monomials that does not contain anything in your ideal, because remember, S are meant to be the cycles, so the minimal ones are the circuits, and if you don't contain a union of circuits, that's when you're independent. So this generalizes the notion you have for Hilbert function of an ideal over a field, if you're familiar with that. And then something that follows kind of automatically from the very definition that these matrices are compatible is that this function eventually, for large enough d, becomes a polynomial in d. Like really, the ranks of the matrix stacking one on top of the other cannot be completely arbitrary. You really, at some point, they need to become eventually polynomial, the ranks at least. So that's something nice. You have some kind of Hilbert polynomial, which is what you would call this for an ideal with coefficients in a field. Something else you can prove is that, well, these ideals are really not finally generated, and I'll say more about this in just if I have time. But they still satisfy some kind of Noetherian condition, which is nice for geometric purposes, meaning that you cannot find an infinite ascending chain of tropical ideals if you fix the number of variables. So even though these are not finally generated in any sense, really you cannot continue growing an ideal and growing and adding more subsets while still preserving this matroidal property. That's not possible. Okay, so these are some of the algebraic things you can prove with these objects. How about the connection between the algebra and the geometry? So what do I mean by the geometry? Well, remember that whenever you have a collection of subsets of n to the n, you can define the variety in the same way we defined it before. Just for every subset in the collection, consider the directions where the maximum dot product with those elements is attained at least twice. And then what we proved is that, well, this is certainly not true. What I'm going to say is certainly not true for any collection of subsets of n to the n. It really needs to, the matroidal property is essential for this theorem to be true, which is that this variety in this sense, it's a finite polyhedral complex, okay? So really you have a finiteness condition, even though you have infinitely many matroids, and each matroid gives you some kind of, imposes conditions like this. The fact that they're compatible means that you can stop at some point, and then from there on you get no more conditions. The other ones are redundant. So you get a finite polyhedral complex, and it turns out the dimension of that complex is related to this polynomial that I told you of how the ranks are growing in the matrix, the Hilbert polynomial of the ideal. So if the ranks are growing quadratically, then you're going to get a polyhedral complex of dimension 2. If the ranks are growing cubically, then you're going to get a polyhedral complex of dimension 3, so on. And if you know a bit of tropical geometry, this took us a while to figure out, which is that this polyhedral complex is balanced, in the sense that not all the cones are looking in one direction, but really if you have a cone in one direction, there should be some other cone that counterbalances in this direction. Good. More recently, we've been working on things like, there's still some connection between the algebra and the geometry. So there is this Null-Stellensatz theorem in algebraic geometry or in commutative algebra that tells you that if you have a polynomial that vanishes on an algebraic variety, then that's because some power of that polynomial is in the ideal that defines that variety. Okay, that's some classical theorem of Hilbert. And here we can prove some combinatorial analog of this that is not implied by the classical one, nor implies the classical one, which is that if you have one of these ideals, these collections of subsets, these tropical ideals, and somehow some subset, the variety of that subset, so this set vanishes on the whole variety, so it contains the whole variety, then that's because some power of this set, and by that I mean just the Minkowski sum of S with itself enough times, m times. Well, maybe not exactly that set, because that set, when you take the Minkowski sum of like the coordinate, the point-wise sum of the set with itself, you might get some holes that are never filled, no matter how much powers of the set you take. But you take the saturation, meaning you fill the holes inside and just take a convex collection of lattice points. That you can ensure that if you let m be large enough, that's going to be an element in your ideal. Okay, let me just tell you one more thing. So one question I had at some point is like, how general can the varieties of these ideals be? So we proved that whenever you have a tropical ideal, one of these towers of matrix, the variety has to be a balanced polyhedral fan, finite dimensional polyhedral object. But how general, if I give you any balanced polyhedral object, is it possible maybe that it's the variety of some ideal? It turns out the answer is no. This is something that we did with Jan Dreisma a few years ago. Not even for Bergman fans of matrix, not even for matroid fans if you take like a non-realizable matroid. So not every balanced polyhedral complex has the form V of I. And what we did, just because I'm running out of time, let me tell you quickly a bit. So the fan that we proved this can never be obtained as the variety of any tropical ideal is the matroid fan of the Vamos matroid direct sum with U2, 3. So a matroid on 11 elements of rank 6. Of rank 6. And the argument was something like, well, if you want the variety to be the matroid fan of this matroid, then you know what the matroid in degree 1 should be, the matroid that tells you what the dependencies are between the 11 variables, monomials without any exponents, like So it needs to be exactly Vamos times U2, 3, but then if you know the matroid in degree 1, well, let's think about what the possible things for the matroid in degree 2 are. And then in degree 2, you have 24 mixed monomials, like that are a product of a variable, one of these 8 variables times with one of these 3 variables. So there's 8 times 3 mixed monomials. And that should be some kind of quasi-product of the 2 matrices, meaning if you have the 24 monomials, so imagine the monomials are like one of the 3 variables in these ones times one of the 8 variables. So think the ground set is kind of a rectangle. And whenever you're restricted to one column, you should always get the U2, 3 matroid. Whenever you're restricted to a row, you should get the Vamos matroid. So it should be a matroid on 24 elements that restricted to rows is always U2, 3, restricted to column, the other way around, is Vamos matroid. But it needs to have rank 8 if you don't want to destroy the variety, if you don't want to impose too many conditions for the variety to still be this fan. And then it turns out that there's an old theorem of Latvernias saying that you cannot do that. There is no, that's what Las Vernias was calling a tensor product of these two matrices, and you cannot find a tensor product, meaning a quasi-product of rank 8 of these two matrices. So I'm telling you this in a bit detail so that you see what kind of arguments go into proving, for instance, that, that not every polyhedral complex is the variety of some ideal. That boils down to existence of products, tensor products, quasi-products of matrices, things like this. Let me just finish with a couple of one or two questions. So first of all, one thing I would really like to know is how can we describe finitely these infinite towers of matrices? How can I email you one of these tropical ideals? With my PhD student, Nick Anderson, we proved that actually there's a lot of them. So for instance, in one variable, already you have uncountably many tropical ideals. And if you have uncountably many, that kind of means that you cannot finitely determine them. But it might just be like the real numbers, right? Like you cannot finitely determine a real number. Still, we send each other real numbers on emails all the time. And what we do is we use the rationals, which you say 0.633, and then it repeats from then on. And that's what I would not know how to do with matrix. I tell you the matrix in degree 1, 2, 3, and then I want to say something like, okay, and from there on, just continue in the same way. I don't know what that means. So how can we finally describe some of them? For instance, how would you describe the ideal? If I tell you some things that I have in degree 1, these circuits, how do I build the whole tower of matrices, ensuring that in degree 1 I get the generators that I want to be there? We don't know how to do that. And then I'll end with another question, which is, this question of how general can the varieties of these tropical ideals be? We saw that, like, for example, what are the matrices whose matrix fans can be obtained as the variety of one of these ideals? That class of matrices contains all realizable matrices, kind of by definition, but it doesn't contain Vamos times U to 3 because of this result that I showed you before. So it's some kind of matrix between realizable and all matrices, and strictly smaller than all matrices. It's closed, it's minor closed. This is a result of Nick Anderson. It's minor closed. It has infinitely many forbidden minors, but we don't know much more than that. So I don't know if it should be closer to a realizable one or closer to all matrices. So for instance, I don't know if Vamos matrix is there. And I'll stop with that. Thank you.
Thank you. We're running short on time, so we'll go directly into next talk.